We've now come across first order differential equations, and we're confident dealing with those. What we're going to look at now, and this is a bit of a mouthful, so brace yourselves, are second order linear homogeneous differential equations with constant coefficients. And to help us get a handle on what each of those separate confusing looking terms mean, I've got a handy little table for you. I've got 4 examples of differential equations, and I'm going to break them apart to show you which of these particular descriptions matches and which doesn't. So for instance, the first one we see there, which involves d3y by dx cubed, that's not a second order differential equation. However, it is linear, it is homogeneous, and it does have constant coefficients. The next one, 5y d2y by dx squared, etc., is a second order equation. It is not linear. It is homogeneous, but it doesn't have constant coefficients. The next one on the list, 2 d2y by dx squared plus 3 dy by dx minus 7y equals 4x. We'll learn how to solve these as well, but not in this video. It is second order, it is linear, it's not homogeneous, but it does have constant coefficients. So it's close to what we're going to be focusing on today, but it's not quite right. And this last one still doesn't quite fit the bill. It's another non-example. It is second order, and it is linear, and it is homogeneous, but it doesn't have constant coefficients. Based only on that information, these examples and non-examples of each of the different properties, I'd like you to have a think and jot down your best description and explanation, or it might just be your best guess at this point, of what each of those 4 categories means. And then see if you can come up with an example for yourself of a differential equation that does satisfy all 4: second order, linear, homogeneous, and has constant coefficients. This is the general format for a second order linear homogeneous differential equation with constant coefficients. A, B, and C are numbers. We can see a y dy by dx and a d2y by dx squared on the left hand side, and we've got a 0 on the right hand side. So we're going to break it apart and look carefully at the technical definition for each piece, and then hopefully that big, long, complicated description will condense into a fairly straightforward idea that we can work with and mess about with. Second order involves the second derivative and nothing more complicated. If you've got a third derivative, then it's a third order differential equation, but if it has nothing higher than the second derivative, it's a second order differential equation. Don't be confused by that strange power of 4 you see in there. Although the example given is a valid second order differential equation, it's not a linear second order differential equation. The power of 4 stops it being linear. The linearity of a differential equation refers to powers of the first, second, third, etc. derivatives of y, including the 0th derivative, y itself. If any of those appears with a power higher than 1, or different to 1, then it's not a linear differential equation. We actually refer to this as the degree of a differential equation, which might be a bit confusing. If you've worked with polynomials, we use order and degree interchangeably, and in fact, in decision maths with graphs and networks, we use order and degree to refer to the same things often as well. But in the case of differential equations, we use the phrase order to refer to the level of the derivative that's been taken, and we use degree to refer to the power of the various derivative terms that we might have. Luckily for us, since we focus on the degree 1 differential equations, we don't need to worry too much about the nuances between degree and order. We stick with the linear ones, where you won't expect to see A, any powers of y or dy by dx that are higher than 1, and B, you won't see anything like y times dy by dx. You won't see any combinations like that. Next, the homogeneity. Is it homogeneous or not? Basically boils down to, can you see a 0 on the right hand side, or could you rewrite it so that it has a 0 on the right? Now obviously you're thinking I could always do that, subtract whatever's on the right hand side, but technically we're looking for multiples of y and its derivatives on the left hand side and nothing else. If therefore you've got something like 4x kicking around that's not tied to a y or a dy by dx, then that would count as a non-homogeneous differential equation. And these are actually still solvable. This non-example here, for instance, is one that you will be able to solve shortly, but we're first going to need to tackle the homogeneous type so that we can make sense of that general method, and then there'll be an adaptation we can use to generalize slightly to the non-homogeneous sort. The last bit, the constant coefficients, is probably the simplest one to get your head around. When we look at the functions in front of y, or dy by dx, or d2y by dx squared, we're looking for constants. So we can have 5 lots of d2y by dx squared, we can have 0 lots of dy by dx, we can have -3 lots of y, and as long as that's all we've got, constants in front of those, we're looking at a constant coefficients differential equation. Now, you'll notice that we don't have a linear function of x on the right-hand side for this particular example. It's not a homogeneous differential equation, this example, because it has a sine x there. Whether or not the equation is constant coefficient is not to do with the type of function we have on the right-hand side. It's all to do with whether we can write the left-hand side in this general form, with a, b, and c being constants. So it's to do with what's in front of y and its derivatives, not to do with what's on the other side of the equation that might involve functions of x. Now, we're going to look into how we can solve second-order differential equations, but we don't dive straight into the generalized second-order linear homogeneous differential equation with constant coefficients. We're going to start with differential equations that are second order, but that you should already be able to solve. So we'll begin with this one, which could have been pulled out of a mechanics textbook from A-level maths, for instance. If your acceleration is the second derivative of displacement, then this could simply be telling you, here's an expression for my acceleration, calculate an expression for my displacement. I'd like you to have a go at solving this. Think of it in terms of reversing differentiation. You're going to need to do some integration in here. But pause the video and try solving it, and think carefully as you go. Have I missed anything? What else do I need to include here? And see what you notice about your solution. Okay, let's go through this one together. We'll start by integrating. We've got a function of x on the right-hand side, so we should be able to integrate both sides with respect to x. And if we integrate the second derivative of y with respect to x, then we should end up with the first derivative of y. This would be, in our acceleration analogy, this would be like turning acceleration into velocity. But you'll notice, hopefully, you remembered to get a constant of integration. So this, if we had an expression for acceleration, this particular constant of integration would refer to something like the initial velocity of the particle. Not exactly that, because in this case we've got e to the power of something, but it's a constant that relates to the initial conditions involved. So unless we knew how fast we were going at the beginning of motion, the acceleration alone doesn't give us any clue as to how fast we're going at any other point. It just tells us how our speed is changing. Now, we've got the first derivative. We do the same thing again. We can get down to the 0th derivative. But something interesting happens here. The constant of integration we had before has now become some sort of linear term, cx. And we've got an additional, different, or at least not necessarily the same, constant tacked on the end. This would be a bit like taking into account the initial conditions for the position of the object. If all you know is about the acceleration, then A, you don't know exactly how fast it's going at any given moment unless you can be told something about its speed at a certain point, and B, you don't know where it is at any given moment unless you're told something about its position at a given point. So this D would be a little bit like, although not necessarily exactly the same as, its initial position. This brings us on to an important general principle. Whenever we solve first-order differential equations, we end up with a single arbitrary constant. When we solve second-order differential equations fully, when we get a complete solution, we end up with 2 arbitrary constants. It's a bit like if you were plotting this in GeoGebra, it wouldn't be sufficient to have just a single slider changing one number. You wouldn't get just a single family of curves. Albeit the families of curves can be complicated for first-order differential equations because the constant may not involve simply translating up and down, it might involve something else, but still it's one slider, whereas now It's kind of like we've got two sliders. We've got the number in front of x can change and the constant can change. And they don't have to be the same. They don't have to be different. They don't have to be there at all. They could both be 0, or maybe just one of them could. And we have a much more complicated family of curves. You can think of it as a two-dimensional family of curves because you can change either of those two constants and you'll still get a valid result. Any and all of the shown cubics, including all the ones you can't see, will satisfy the given differential equation. If you differentiate that expression twice, you'll find it always comes out to give 6x add 2e to the 2x. Now, there are also certain differential equations that you can solve by inspection. In other words, that classic mathematician's trick of looking at a question and then telling you the answer. It's infuriating if you're not the one doing it. We start by looking at something like this. Under what conditions would the second derivative be the same as the first derivative for a function? Can you think of something, y equals some function of x, where the derivative of your function is the same as the second derivative of your function? There's a few more examples a bit like that. When is the second derivative the same as the original function? When is it the negative of the original function? When is the second derivative plus 2 helpings of the first derivative plus the 0th derivative, the function itself, equal to 0? When do they all combine and cancel out entirely? And I'm going to put up a few clues in a second, so if you want to have a go at these four before you get any hints or clues, then please pause the video at this moment and see how much headway you can make. See if you can come up with the functions that will solve these. But if you want the clues, they're coming up now. There are a few common functions you've come across where the derivative is similar in some way to the original function. Now the obvious one that should spring to mind is e to the x. E to the x differentiates to itself. So anytime you've got derivatives connected to other derivatives, e to the x is likely to be hiding there somewhere in the background. Trig. Trig works in this nice cycle. Sine goes to cos, goes to minus sine, goes to minus cos, goes all the way back to sine again. So every 4 derivatives that you take, you get right back where you started. And if you've come across hyperbolic functions, you'll have found this slightly more efficient cycle. Sine differentiates to cosh, which in turn differentiates to sine. So it might be that you can make use of some of those properties and see how some of those things will connect to the 4 questions on the left. That should be enough for you to have a stab and see how you get on with those. Make sure you pause the video and try those for yourselves before you continue. I'm going to be showing some solutions next. So, for the very first one, probably the first one that springs to mind for you is the first one that sprang to mind for me, y equals e to the x. If it's a function that differentiates to itself, then of course its second derivative must match its first derivative. And you could even, in this case, integrate both sides and get dy by dx equals y. And if you integrate both sides again, well, you'd have some difficulties because you have dy by dx equals y. You can't integrate y with respect to x, but perhaps you could use separation of variables, call it 1 over y dy by dx, and then you could go ahead and actually solve directly. You would end up with y equals e to the x, more or less. You'll have to try it to see exactly what I mean by more or less. For the second one, the second derivative equals the original function. Maybe you've used exactly the same result as you did for part A. I've used cosh x just because I can. The first derivative doesn't match the original function, but the second derivative does. For part C, we can use something like sine. If you differentiate twice, you get something which is not the same as the original, but the exact negative of the original. And for part D, takes a bit more work, but if you've persisted with it, you should find you end up with something like e to the minus x. This works well. Because although the first derivative and the second derivative are different, the second derivative is the same as the original. Minus e to the minus x is the same as e to the minus x. However, you may well have come across other functions that also solve these. Remember, we already mentioned that the general solution to a second order differential equation should have 2 arbitrary constants. A complete description of the entire general solution should always have 2 arbitrary constants. So unless we've got those arbitrary constants built in, all you're seeing is an example of one possible solution. It's like solving an inequality and saying, well, it works when x equals 5. Well, that's fine. But if it actually works whenever x is greater than or equal to 2, I'd like to know that. So the general solution is a way of describing not just some examples of when it works, but a general pattern of all the possible functions for which it is true. Have a go at finding some more functions. You might already have some that are different to mine. See if you can generalize them a little bit. See if you can come up with anywhere you could put an arbitrary constant where it wouldn't affect the validity of your solution. See how general you can make it. Let's look at a few more solutions that I've found for these 4 differential equations. For part A, I also found y equals 3. That works just as well as y equals e to the x. Think about it. If you differentiate 3, you get 0. If you differentiate 0, you get 0. So the second derivative is the same as the first derivative because they're both 0. Now, if that works with e to the x and it works with 3, what do you think would happen if we tried e to the x plus 3? Well, the first derivative would be e to the x, and the second derivative would be e to the x. In other words, what happened to make e to the x work still happens, and therefore it still works, and what happened to make y equals 3 work still happens, and therefore that bit still works. And if each separate bit of the function works, then the whole thing works. And it's a bit counterintuitive, but it turns out we can combine solutions for differential equations by adding them. Provided we've got homogeneous differential equations, which these are, we can put functions together to generate new functions. And if the original functions were solutions, then so are the new ones. We have to put them together in certain ways. You can add them, you can't necessarily multiply them. But hopefully you can see something like 5e to the x minus 4. If you differentiate it twice, the 5e to the x is unchanged by that process. The minus 4 disappears straight away as soon as you differentiate, and it will still not be there when you differentiate a second time. So the first and second derivatives will both just be 5e to the x. We can see it more generally with this graph here. If you've got some multiple of e to the x, and then you add a constant, that doesn't affect the gradient, and it doesn't affect the gradient of the gradient. We can also mess with how much of an e to the x we have, and that still doesn't mess things up when it comes to comparing the first and second derivatives. As long as all we need is for the first derivative to match the second derivative, then any multiple of e to the x will work, any constant will work, and crucially, the sum of those two things will also work. Now looking back at our questions, part B, cosh x we had. Well, unsurprisingly, sin x will work just as well. Differentiate once, you get cosh. Differentiate it again, you get sin. But it turns out e to the x will also work here. This might have been the first one you wrote down. If we want something whose second derivative matches the original function, well, e to the x, all the derivatives match. So that's a nice simple one. You might not have noticed e to the minus x works in this case as well. If we only need the second derivative to match, e to the x, e to the minus x, they work in a similar two-way cycle to cosh and sin. You might want to look at the definitions of cosh and sin to see why that happens the way it does. E to the x and e to the minus x are not fundamentally different objects to cosh and sin. Cosh and sin arguably are just a different way of writing something that involves e to the x and e to the minus x. It turns out you can put these together in different ways, just the same as we did for the first question. We can have some multiple of e to the x, and it will work just fine. We can have a multiple of e to the minus x. We can have a sum of those two things, and that will still work. What about part C, y equals sin x? Well, cos works just the same. You can differentiate twice, and you'll get the negative of what you started with. And more generally, we could even write this as some constant times sine plus some constant times cos. That's because if sin x works, then so does 2 sin x. When you differentiate, the 2 is preserved. It stays in front, just like the example we've got on the graph, where the number in front of e to the x doesn't change. And that also holds true for the cos bit. But if it works for sine and it works for cos independently, then you can add the two and you get something that still works. You can try this out for yourself. I would recommend you test it. Try sine plus cos, something simple, and see what happens when you differentiate. Because each bit of the function, each separate term, satisfies the overall differential equation, the whole thing will. And it works because we're dealing with a homogeneous differential equation. If we can put derivatives of y all on the same side of the equation and get an equals 0 on the other side, we can add functions that satisfy the equation, and we'll just get more functions that satisfy the equation. The last one was tricky to find a solution for. It takes a bit of work to notice that e to the minus x works. But once you've found it, well, here's another one that you're unlikely to have found. X e to the minus x. It's not an obvious solution by any means, certainly not to me. It's not the sort of thing I would normally think of to try. But once you've played around with these second order differential equations for a while, you'll realize that this is a sensible sort of thing to test to see if it might work. And very often it will. You'll need to test this one with product rule to convince yourself that it actually does the job, but it does. X times e to the minus x, you can differentiate it using product rule. You can differentiate the result again using product rule and see that it does actually satisfy this differential equation. And if that's the case, you could have any multiple of e to the minus x combined with any multiple of x e to the minus x, and that would also satisfy that differential equation. And it's this last type, the type that we can see in part D, that we're going to be focusing our attentions on. This is a second order, linear, homogeneous differential equation with constant coefficients. In fact, all four of these are, and we'll come back and look at all four of them later once we've got a general technique. But this last one is the one that's most obviously the general type of thing we're dealing with. It's got second derivative and a first derivative and a zeroth derivative all involved in that. And it's non-obvious to find the general solution. That's the process we're going to look at next. But this fundamental principle that we need to make sense of, that we've hopefully picked up from this exercise, is called the principle of superposition. If you are dealing with the solution to a homogeneous differential equation, not only can you scale up your solutions, if y equals f of x works, then y equals a times f of x will also work. Not only can you scale up your solutions, but you can also add your solutions. And the most general version of this is the bit right at the bottom here, where we say if f of x and g of x both work, so does something times f of x plus something times g of x. It's a really important idea, and it will allow us to combine different solutions to a differential equation to generate a fully generalized solution to a differential equation. We've seen a couple of these already here. Anything where we've got an a and a b, it's basically the fully generalized solution to the differential equation. Something times sine x plus something times cos x. No matter what those two somethings are, you'll find that the result satisfies this differential equation. And similarly with the last one, if y equals something times e to the minus x plus something times x e to the minus x, it will definitely satisfy the second order differential equation we started with. Now we're going to look into something called the auxiliary equation. This is a really useful trick for dealing with those more generalized second order differential equations. Let's start with this example. Y double dash plus 5y dash plus 6y equals 0. The first thing I want to do is guess the general format of a solution. This is a very common technique generally when dealing with differential equations. You've seen a similar thing with things like partial fractions, where we're trying to predict what sort of thing we can end up with, and then we leave some things as constants that we can figure out as we go along. So in this case, let's guess something logical. Given that we've got a combination of derivatives, let's pick a function that behaves nicely under differentiation. We're going to try e to the x, but of course e to the x itself is a bit too specific. E to the something x is going to be a better suggestion because the derivatives are closely related to each other, but they're not exactly the same as each other. If they were the same, then the second derivative plus 5 lots of the first derivative plus 6 lots of the 0th derivative would not give you 0. But perhaps with the right value of m, e to the mx being equal to y could give us something that would work. Let's try this. If y equals e to the mx was a solution, then we could find the first and second derivatives. That doesn't take us too long. We get the first derivative, often referred to as y dash to make our notation a bit easier. The first derivative will be m e to the mx, and the second derivative will be m times m e to the mx. Once we've got those, we know that y equals e to the mx is a solution. Well, that's the assumption we're starting with. So we can substitute it into that differential equation. If we do that, this is what we get. M squared e to the mx plus 5m e to the mx plus 6 e to the mx equals 0. And then the next logical thing we can do is factorize. We can pull out e to the mx as a common factor of everything, which is handy. And then you'll notice that what's left behind is a quadratic. The m squared comes from the second derivative term, the m comes from the first derivative, and then the constant comes from the 0th derivative. So the powers of m directly correspond to the order of the derivative term that we took. This makes it really quick and easy to generate that quadratic. So if you're looking at a differential equation and you can pick out the constants in front of the second derivative, the first derivative, and the 0th derivative, then you've got the constants in front of m squared, m, and the number. So why is that useful? Well, let's continue factorizing and we'll see. E to the mx times m add 2 times m add 3 equals 0. Well, we've got three factors that multiply to make 0, and the zero product principle tells us that anytime you've got a bunch of numbers that multiply to make 0, we know for sure that at least one of those numbers must be 0. That's the only way that can happen. So to find all possible solutions, we need to investigate each of our three factors. We can rule out e to the mx straight away. It's e to the power of something, so it can't be 0. That leaves us with just two solutions, m equals -2 or m equals -3. Let's go back and let's put them back into the original y equals e to the mx. Y equals e to the -2x and y equals e to the -3x. Both of those you could verify are valid solutions to the original differential equation. You can take the first and second derivatives and you can put them back in and you'll find that they work. But we can now apply that principle of superposition that we saw before. We can take any multiple we like of e to the -2x, and that will also be a valid solution. We can get any multiple we like of e to the -3x, and that will be a valid solution too. And then we can add those two things and get an even more general solution. Any multiple of a solution is a solution, and the sum of two solutions is a valid solution, provided we're dealing with a homogeneous differential equation like we are. So the general solution must be a e to the -2x plus b e to the -3x. This is our solution. We know that it's likely to be the right kind of solution because we have two arbitrary constants involved. And anytime you've got a second order differential equation, we're expecting two arbitrary constants in our final general solution. If you haven't got two, then you're not done yet. You need to be looking further afield. You need to find more solutions, really, more different solutions so that you can generate for yourself essentially a two-dimensional family of solutions. Another thing that's sometimes asked for in these questions is the long-term behavior of a function. And once you've solved it and you know what y is equal to, you can often answer this long-term behavior question without ever knowing what a and b are. We don't care whether a is positive or negative, whether b is positive or negative. We don't care which one is bigger than the other one. All that matters here when we look for long-term behavior is what happens as x gets, let's say, large without limit. So as x approaches infinity, what happens to y? In this case, y tends to 0. Both of those terms are exponential decay curves. E to the -2x and e to the -3x are both tending towards 0 as x tends to infinity. And it makes no difference whatsoever what the constants a and b are. That's still going to be the case. Now, in terms of x tending towards negative infinity, it kind of depends on the sign of capital A and capital B, exactly what's going on there. And in fact, the general shape of the graph varies quite a bit depending on how many helpings of e to the minus 2x you pick and how many helpings of e to the minus 3x you get. But I'd encourage you to mock it up on GeoGebra and see what it ends up looking like. Here's one example that I've come up with. If we have minus 5e to the minus 2x and a positive 2e to the minus 3x, this will be an example of a particular solution to the differential equation that goes through the point 0, minus 3. You can see it has some interesting behavior close to 0, comes down from positive infinity, and then it has a minimum point before going up towards an asymptote at 0. We can see for this particular example, and you can test it for other examples as well, regardless of what it does early on, the long-term behavior will always be the same. As x tends to infinity, y will tend to 0. And of course, you can check your solution in general by finding the first and second derivatives and substituting back in the original equation. Now, let's see if we can generalize this method. Let's look not at a particular second-order linear homogeneous differential equation with constant coefficients, but at a general version where the constants are replaced with a, b, and c. If we assume that a solution of this form exists, then we can find the 0th, first, and second derivatives. Then we can substitute back into the original differential equation, factorize. Then we need to make a bit of a leap, and it's going to be messy if you decide to start using the quadratic formula. So what I'm going to suggest here is that we make an assumption that the quadratic we end up with has two solutions, and that those two solutions are alpha and beta. And then from there, I'd like you to write the general solution in terms of alpha and beta. Have a go at doing these steps. It'll help you to see how well you've made sense of the previous example. When you're ready, unpause the video and we'll work through them step by step. Let's begin with this. Y is e to the mx, the derivative is m e to the mx, and the second derivative is m squared e to the mx. If we substitute into the original differential equation, we get this, a m squared e to the mx, etc., etc. When we factorize, we can pull out e to the mx, and we're left with this quadratic, a m squared plus bm plus c equals 0. This is the important bit. This part here is an equation which tells us about the original differential equation. And the two solutions that we've assumed we got, alpha and beta, those are the solutions for m, so we go back and we say, well, that means that y equals e to the mx is actually y equals e to the alpha x, or for the other root, y equals e to the beta x. And because of the superposition of solutions, we can have any constant multiple of each of them added together. So this is our general solution. Now, we've made a couple of assumptions in here. Can you see when the approach might fail? Can you think of a situation where we would struggle to form a general solution that looks like this? Have a think about that. It's to do with the quadratic that we're dealing with. Speaking of which, this particular quadratic equation is what we're talking about when we refer to the auxiliary equation. Auxiliary equation because it's an equation which is related to and yet not equivalent to the original second-order differential equation. The a, the b, and the c are exactly the same constants as appeared in front of the second derivative, the first derivative, and the 0th derivative. So this trick of making the assumption of what y could be and then going through and solving basically allows us to generate the general solution for any second-order linear homogeneous differential equation with constant coefficients. The roots of the auxiliary equation determine the parameters for the general solution. The alpha and the beta that we would get if we solved that differential equation, if we solved the auxiliary equation, the alpha and the beta that we get by solving the auxiliary equation tell us the alpha and the beta that go into the general solution for the original differential equation. So to clarify, we have a second order differential equation with constant coefficients that should look something like this. And the auxiliary equation looks very, very similar. The second, first, and zeroth derivatives of y are essentially swapped out for the second, first, and zeroth powers of some variable like m. And somehow the roots of the auxiliary equation determine the parameters that go into the solution to the differential equation. Not only that, we're now going to look into how the nature of the roots of the auxiliary equation determine the format of the solutions to the differential equation. What do I mean by that? Well, a quadratic equation doesn't necessarily just give you two different real roots every time. We already know there are actually three different situations you might be in, and each needs to be treated differently. We could use the discriminant to determine which one we're looking at in any particular case if we needed to. But we might have two distinct real roots, and that's the situation we've already seen. So if, for instance, we ended up with m equals -2 or m equals -3, we can generate our general solution by taking e to the -2x and e to the -3x and applying the principle of superposition. We'll have any multiple of e to the -2x plus any multiple of e to the -3x, and there's your two-dimensional solution family. Y equals a e to the -2x plus b e to the -3x. But what if we'd ended up with the same solution twice? Well, it wouldn't be a lot of good having a e to the -2x plus b e to the -2x, because e to the -2x will be a common factor, and you just have a plus b times e to the -2x. You've not then got a combination of two different exponential curves. You've just got one exponential curve and a fairly pointless a plus b that gets multiplied by it. A and b don't then give you a two-dimensional family of curves, because no matter what a and b are, all that matters is the sum of a and b, which is itself just a single arbitrary constant. That is where we need a slightly different approach. We need to find another way of finding a solution. And it turns out there is another solution that works. If you're dealing with a repeated root, then e to the alpha x will be a solution, but x e to the alpha x will also be a solution. This might remind you of one of the examples we had earlier when we were looking at solutions by inspection. Turns out we can have a e to the alpha x and bx e to the alpha x. The last one of the three cases is complex roots, and this one's even crazier, because this one somehow involves trig as well as exponentials. So you can be forgiven for thinking that these three are sufficiently different to each other that there's no obvious connection between them. It turns out, as you might expect, mathematically speaking, there is a connection between them. It's a little messy, and it's not the sort of thing that I want to try to go into during a video. It's better shown face to face, but it's also a good one for you to try on your own to get a sense of what's happening. You can make some decent headway with this if you follow the right sort of process. So for the real and equal roots, demonstrating that x e to the alpha x is a solution is essentially the crucial part of this. We need to find something which is different to just e to the alpha x and yet is also a solution. And it turns out if you differentiate x e to the alpha x a couple of times, find the first and second derivatives, we can show that a y double dash plus b y dash plus c y will be 0 when y is x e to the alpha x. And it's only true because alpha is a repeated root of the auxiliary equation. It takes a bit of work, but you can demonstrate that if you work through it. And once you've got that, because x e to the alpha x is a different object to just e to the alpha x, we can add a multiple of one and a multiple of the other one, and we've got our general solution with two arbitrary constants. For the complex numbers one, you can probably guess, if you've recently looked at de Moivre's theorem and you've looked at Euler's relation, you'll realize there's something fundamental that connects exponentials and trig, and the something fundamental is imaginary numbers. If we're dealing with imaginary numbers, in this case, we'll have complex conjugate roots for our quadratic equation, because a, b, and c will be real numbers when we're dealing with them here. And that means we'll have p plus or minus qi. And we get this crazy beast, e to the px times a cos qx plus b sine qx. The p, with the exponential at the beginning, is the real component of the complex number, and q is the imaginary component. It'll be plus or minus in the roots. All we care about is the size of that number. What I'd recommend for this one, if you want to give this a go, is to try to demonstrate separately that e to the px cos qx is a valid solution, and so is e to the px sine qx. And when you've convinced yourself that they both work, then we can see that adding multiples of each one together will give us the general solution. There is, again, a nice way of showing how we can derive this directly by using the e to the root times x process from the original version that we had. It takes a bit of work and you need to play around a bit with the constants, but it's quite nice to see where it comes from instead of just taking it on faith. However, all you need to be able to do in an examination for this is to identify which of the three formats you need, whether it's real and distinct roots, real equal roots, so repeated root we might call it, or whether we're dealing with complex conjugate roots. And in each case, select the appropriate format and put the correct value for alpha or alpha and beta, or for p and q, into that format. Now we're going to revisit the four differential equations we previously solved by inspection, and we're going to get a little bit of practice using our new technique. So remember, the key idea is that we can write down the auxiliary equation. That should be very quick to do. We recognize the 0th, first, and second derivatives to be equivalent to the 0th, first, and second powers of some constant like m. When we solve for m, the nature of the roots tells us the format of our general solution, whether the roots are real and distinct, or whether the roots are repeated equal roots, or whether they are complex conjugates. And then the value of the roots tells us the parameter that we need to put into those general solutions. So they're written out here for you. You will need to learn them eventually, but for now you can refer to the list on the screen. I'd like you to pause the video and have a go at all four of these, rearrange them a little bit if you need to, so you can write out the auxiliary equation in each case and see if you can come up with the fully general solution to each of these differential equations. So initially, probably the simplest way to write these down would be in the y dash form, y double dash minus y dash equals 0, etc., etc. You can do that for each of them, and it'll probably save you a fair bit of writing time. Next, we need the auxiliary equation. So instead of the second derivative, we'll have m squared, and instead of the first derivative, we have m. M squared minus m equals 0. We can do a similar thing for the next one, but instead of y, we have 1. Easy to make a mistake with this one. Think of it as the 0th derivative of y, so we need m to the power 0. The next one's very similar, m squared plus 1 equals 0, and the last one looks a bit more like a full quadratic with the m squared term, the m term, and the constant. Now in each case, these can be solved very quickly and simply. The first one, we have two distinct solutions, 0 and 1. The second one, we've also got two distinct solutions, plus 1 and minus 1. The third one, our two solutions are actually complex numbers. They are conjugates, 0 plus 1i and 0 minus 1i. But actually, these ones are purely imaginary. You might want to think about what happens to the complex roots format when we have no real component going on at all. And then the last one, this is a repeated root. I've written it twice for emphasis, but if we factorize, we get m plus 1 in a bracket squared. So m is equal to minus 1 or minus 1 again. In each case then, we've got a particular scenario we need to use. Distinct real roots for the first two, and the next two get a bit more complicated. But let's just check for the first two that we understand what's happening, because that first one doesn't look quite like the general format. A plus b e to the x. If you look carefully, you'll notice though, a e to the 0x is the same as writing just a. So if you remember, when we found that things like y equals 3 satisfy this differential equation, that is an example of b equals 0 and a equals 3, a special case of this general equation. For the second one there, a e to the x plus b e to the minus x. And if you wanted the examples we had before, like Shine and Kosh, you just need to select sensible values for a and b. You could have a half and a half, or half and minus a half, for instance. But you could also select any other numbers for a and b, and you would find equally valid solutions. When we get to c, we have complex conjugate roots, so we're going to need the one with the trig involved. But because the real part is 0, we have e to the 0x in front of the bracket. And as we saw from the first one, e to the 0x is just 1. So the bracket becomes the only bit that matters. 1 times whatever's inside, which is trig. A times cos of qx plus b sine qx. And q is the imaginary component. Here, you've got to notice that we won't end up with any imaginary numbers in our final solution. That's deliberately done. It's possible to generate imaginary functions that solve these differential equations, but we're interested in real valued functions because we're looking at these as real valued differential equations. But q is just the number in front of I. So we have 0 plus 1i and 0 minus 1i. That means p is 0, but q is 1. So we'll have a cos 1x and b sine 1x. Which means any multiple of cos x and any multiple of sine x added together will work. For the last one, we have repeated roots. So we're going to use the fact that instead of just a constant times the exponential for one of the roots and a different constant times the exponential for the other, we'll need not just e to the power of alpha x, but x e to the alpha x. That should always also be a solution when alpha is a repeated root. So we can make use of that, and we have something linear, a plus bx, multiplied by e to the power of alpha x, or in this case, e to the power of minus x. You should now be able to tackle all of the questions from exercise 7b. Each of these is focusing on a homogeneous case of a second order linear differential equation with constant coefficients. Once we've done this, we'll move on to the non-homogeneous situation, where we take advantage of the results we've got here, and we generalize a little bit. We find a way of adding on a bit that lets us solve a more general form of differential equation.